Welcome to the deep dive. We got a bunch of sources from you about construction efficiency, and today we're really zeroing in. We're going to dig into the big one for electrical safety, the National Electrical Code. That's right, the NFPA 70, specifically the 2023 edition. And we're focusing on Chapter 2, Wiring and Protection. This chapter really sets the stage for how power gets managed in buildings.
It does, but we're not reading the whole chapter, obviously. Our mission today is actually to pull out this really practical, kind of specific shortcut the code offers.
Whoa, for what kind of setup?
For new restaurants. It's a surprisingly efficient way to handle a very common commercial project.
Okay, that sounds useful. Anyone who's done electrical design knows the standard load calculations. The ones in Part 3, they can take ages.
Oh, yeah. You're calculating lighting, specific appliances, outlets, HVAC, and applying all these different demand factors. It works, but it's slow.
Right, very methodical.
Yeah.
So what's this shortcut?
It's Section 220.88. The title is literally Optional Load Calculation for New Restaurants. And here's the key. It lets you bypass that whole detailed Part 3 calculation.
You just skip it.
Well, you calculate the entire service or feeder load using just one table instead. Table 220.88. It's like the code is saying, look, we know new restaurants generally have predictable peaks, so here's a faster way.
As long as it's a new restaurant installation, right?
Exactly. That's the condition. So the big win here is simplicity, saving time. But, whenever the code gives you an optional path, there are always some rules attached.
Always guardrails. So what are the key safety things we absolutely can't skip, even with this shortcut?
Good question. The code is clear. You simplify the calculation, not the fundamental safety. For instance, protecting the service conductors against overload. That still has to follow sections 230.9 and 240.4.
Okay, so the shortcut helps size the wires based on expected demand, but the actual protection, the breakers, the fuses, that's still based on the wire's limits and fault currents. Makes sense.
Precisely. Basic system protection isn't optional. And another point in 220.88 clarifies the feeder conductors.
What about them?
It explicitly says the feeders don't need to have a higher ampacity than the service conductors you calculate using this method. They're sized together based on this optional load.
Got it. And you mentioned something critical about the neutral wire calculation before we started recording. That's handled differently.
That's right, yeah.
Yeah.
Even if you use 220.88 for your main load, calculating the neutral load, that bounces you back to section 220.61.
Why the separate rule for the neutral?
Well, think about it. Neutral sizing is all about system balance, right? And potential harmonics from things like electronic ballasts or VFDs. The 220.88 shortcut is great for predicting total power demand, but it doesn't really see those tricky current interactions on the neutral.
Ah, so it's a statistical shortcut for the hot legs, but for the neutral, where currents might add up weirdly instead of canceling, the code says, nope, use the standard, more detailed method.
Exactly. It's balancing that high-level efficiency with fundamental safety physics.
Fascinating distinction. Okay, let's get into the core of it then. Table 220.88. How do you actually use it? What's step one?
Step one sounds simple, but you have to be thorough. You calculate the total connected load in kVA, and that means everything.
Everything, like heating, cooling, cooking, lights, the lot.
The whole shebang. Every single electrical load gets added up into one big number. No skipping the walk-in cooler or the HVAC unit.
Okay, so total connected load first. Then what?
Then you take that total kVA number, find where it fits in the table's ranges, and this is crucial. Figure out if you're dealing with an all-electric restaurant or a not all-electric restaurant.
That distinction seems pretty important.
It's the main distinction in the table. Once you know your total kVA and which column applies, you pick the one calculation rule for that row. Multiply your total connected load by the demand factor, or use the specific formula given. That result, that's your final calculated load for the service or feeder.
Right, so it all hinges on that all-electric versus not all-electric choice. Let's break that down. The code is essentially applying different diversity factors based on the fuel source, isn't it?
Pretty much. It's reflecting decades of data on how likely equipment is to run simultaneously. Let's look at the first scenario. Smaller places, 0 to 200 kVA total connected load.
How does it play out there?
Okay, if it's all electric, the code gives you a nice discount right away. The calculated load is just 80% of the total connected, a 20% reduction.
Recognizing not everything's on at once, but what about the not all electric in that same range? Gas stove, maybe?
If you've got gas or other fuels for major appliances, it's different. Below 200 kVA, the calculated load is 100% of a total connected load.
Wow, no discount at all, 100%. Why so conservative for the next fuel places?
Well, the thinking might be that in a smaller place, even with gas cooking, the electrical stuff, refrigeration, ventilation, maybe some prep equipment, lights, they're probably all running near full tilt during peak hours. There isn't enough electrical variety yet for a big diversity discount.
Whereas if it's all electric, even in a small place, you've got more electric things competing, so some diversity kicks in immediately.
That seems to be the logic, but then things get a bit more complex once you go above 200 kVA. Let's look at the mid-range, 201 to 325 kVA.
Okay, what happens here?
For all electric, the discount gets huge on the additional load. The rule is 10% of the amount over 200 kVA plus a base of 160 kVA.
Only 10%. That's a massive 90% diversity factor on that chunk of load over 200 kVA.
It is. Now compare that to the not all electric in the same 2-on-1 325 kVA range.
Let me guess, it's higher.
Much higher. It's 50% of the amount over 200 kVA plus a base load of 200 kVA.
Okay, wait, so the multiplier is way higher, 50% versus 10%, and the starting base load is higher too, 200 kVA versus 160 kVA.
Exactly. That's a significant difference just based on whether the cooking is electric or gas.
Why would the non-electric baseline jump up like that, the 200 kVA base versus 160?
It suggests the code assumes that even in a gas kitchen, there's a pretty substantial chunk of fixed electrical load running constantly before you even get to the bigger, more diverse loads. Think about it. Huge exhaust hoods, makeup air systems, complex controls, maybe pumps, specialized lighting.
Stuff that runs regardless of whether the gas burners are on high or low.
Right, so that higher baseline acts like a buffer, ensuring enough capacity for those critical non-cooking electrical systems.
Okay, that makes sense. It's covering the essential electrical infrastructure. Let's move up. Scenario 3, high range, 326 to 800 kVA. These are pretty big restaurants.
And the pattern kind of continues, but shifts a bit. For all electric, the calculation is now 50% of the amount over 325 kVA, plus a base of 172.5 kVA. Notice the percentage jumped back up.
Yeah, from 10% in the previous tier up to 50% now for the load over 325 kVA. Interesting. What about the not all electric side?
For not all electric, the multiplier actually drops slightly to 45% of the amount over 325 kVA. But look at the base load.
Let me see. 262.5 kVA. Much higher again than the all-electric base of 172.5 kVA.
Consistently higher base requirement for the non-electric option, even when the percentage multiplier for the extra load gets closer, or even a bit lower like here.
So the code is essentially saying, if you use gas, we need you to build in more guaranteed base electrical capacity right from the start, front-loading it like you said.
Seems that way. Now the final tier, the really big places. Scenario 4, over 800 kVA total connected load. This is where demand factors really earn their keep.
Okay, the giants. What's the calculation for all electric?
It stays consistent. 50% of the amount over 800 kVA plus a base of 410.0 kVA. So that 50% demand factor holds steady for all the load above 800 kVA.
But the not all electric side.
Yeah.
You flagged this one earlier. What happens there?
This is the most dramatic shift in the whole table. For a not all electric place over 800 kVA, the multiplier absolutely tanks. It drops to just 20% of the amount over 800 kVA.
20%. Seriously.
Seriously. Plus a base of 476.3 kVA. So once a mixed fuel restaurant gets truly massive, the code assumes the additional electrical load above that 800 kVA mark is incredibly diverse.
Like, it's mostly lighting, maybe huge banks for refrigeration, IT systems, convenience outlets. Stuff that's very unlikely to all peak at once compared to the core kitchen load, which is partly gas anyway.
Exactly. So only 20% of that extra load needs to be factored into the service size. That is a huge saving in terms of equipment size and cost compared to applying a higher percentage.
That 20%, wow. That's the code, fully embracing diversity in large-scale commercial operations. It prevents massive, expensive oversizing for loads that statistically just won't run together.
It fundamentally changes the game for designing those really big facilities. Keeps it safe, but makes it practical.
Okay, let's wrap this up. We took this deep dive into NFPA 70, Chapter 2, looking at wiring and protection, and specifically drilled down into Section 220.88. And what we found is this really powerful specialized tool.
Yeah, this optional load calculation, it gives you a very targeted way to size electrical systems for new restaurants.
Using demand factors that are completely tailored based on just one key question. All electric or not all electric?
Right. It's the code trying to balance those real-world operating assumptions, how restaurants actually use power with the non-negotiable safety rules.
So the big takeaway for anyone listening, especially if you work on these kinds of projects, is that this shortcut exists. It can save significant time and potentially cost, but you've got to apply it correctly based on that all-electric not all electric split. And remember the specific caveats, like the neutral calculation.
Absolutely. And maybe a final thought to leave you with, digging into that pattern we saw. Think about this. The not all electric restaurant always had higher required base kVA at the start of each tier in the table, right?
Yeah, that 200 versus 160, the 262 versus 172.5, consistently higher starting point.
But then for the largest loads, over 800 kVA, it got that dramatically lower percentage multiplier, only 20%.
Yep.
So what specific assumptions about how a gas kitchen operates versus an all-electric one led the NFPA committee to structure it that way? Higher initial demand, but much greater diversity assumed for the biggest loads.
What's running in that mixed fuel place that demands more base capacity but diversifies faster at the top end?
Exactly. What's the underlying operational model that results in that specific mathematical pattern in the code? That definition of demand factor in action. It's worth pondering.